today's lesson is about the differentials. At the end of this lesson, you should be able to determine the differential of a function and to use it to estimate the value of a function using local linear approximation. To define what a differential is, let us have y a differentiable function on some open interval containing x. The differential of x that is denoted by dx is any non-zero real number. The differential of y denoted by dy is defined to be equal to the product of f prime of x times dx. To work out the differential of some differentiable functions u and v, we have this differential formula. So let us have u and v be differentiable functions of x. On this basis, we have the differential of a constant times the function u is equal to the constant c times the differential of u. The differential of the sum or difference of the functions u and v is equal to the sum or the difference of the differential of u with the differential of v. For the product u times v, the differential is given by u times the differential of v plus v times the differential of u. And working out the differential of a ratio u divided by v, we have this equal to v times the differential in u minus u times the differential in v all over v squared. Let's now apply this concept of the differentials to determine the differentials of some functions. So for our first example, we have to find the differential of y equal to x cubed plus 5x minus 1. Now, based on the definition of the differential of y will just be the differential of the right member x cubed plus 5x minus 1. Now, in practice, what we do is simply get the derivative of the right member of the equation and multiply this with dx. So that dy will just be equal to the product between 3x squared plus 5 and dx, where 3x squared plus 5 is the derivative of x cubed plus 5x minus 1. The differential dy can also be expressed in this manner, where we multiply these terms with dx to give us 3x squared dx plus 5 dx. Working on another example where we need the differential of y defined as ratio of 2x to 3x minus 1. Again, the differential dy is obtained by multiplying the derivative of 2x divided by 3x minus 1 with dx. So differentiating on 2x divided by 3x minus 1, the derivative is given by 3x minus 1, the denominator, times the derivative of the numerator, which is just a 2, minus the numerator 2x times the derivative of the denominator, which is just equal to 3. This is to be divided now by the square of 3x minus 1. So the differential is equal to the product of this expression with dx. And if we simplify the derivative of the function y, that would just simplify 2 and negative 2 over the square of 3x minus 1. Hence, dy is equal to negative 2 over the square of 3x minus 1 times dx. The differential can be used to approximate the value of a function using local linear approximation method described as follows. That if we are given a function y is the f function of x, to approximate the value of y at the value x sub 2, we choose a convenient value of x to start with. Let this be x sub 1. Now we choose x sub 1 to be relatively close to x sub 2 so that the increment delta x would be approximately 0, or delta x approaches 0. Now to approximate the value of y at x equal to x sub 2, we make use of this particular formula, that the value of y at x sub 2 is equal to y sub 1 plus the increment delta y. Okay, or we can approximate this value in terms of y sub 1 plus dy, where dx or delta x is the difference x sub 2 minus x sub 1. Now please take note, the differential in x and the increment in x are equal. dy is equal to f prime of x dx, and this should be evaluated at x sub 1. Please take note that dy, the differential dy, is not equal to delta y. However, the value of dy can be made as close as possible to delta y. Hence, it can be used to approximate delta y whenever dx or delta x is set to be very small, approaching 0. Now let us use the concept of the differential to estimate the value of the cube root of 26.55 using local linear approximation method. Now you may wonder why we're using an approximation method for the cube root of 26.55, whereas you can easily use technology not to determine this value. However, when you do not have technology at hand, then this particular method would come in handy. So what we do first is to determine the function to work with. And since we are asked for the cube root of 26.55, then the function to work with is the cube root function, where f of x is equal to the cube root of x. The next step is to determine x, that is a perfect cube, because we are dealing with the cube root function. Okay, a perfect cube value that is closest to 26.55. That would be 27, and we assign this as x sub 1. Now remember to pick a value that is closest to 26.55 because we want delta x or dx to be approximately 0. So with this, we now can compute the differential dy in terms of f prime of x dx, where the derivative of the cube root of x is given by 1/3 times x to the negative 2/3. Hence, the differential dy will just be product of 1/3 times x to the negative 2/3 times dx, or you can express it in this form. Now with x sub 1 equal to 27, y sub 1 would be equal to 3, that is just the cube root of 27. And using x sub 1, 27, and x sub 2, 26.55, we compute for delta x given by x sub 2 minus x sub 1. Now remember that is also equal to dx. And this will be the value, the difference between 26.55 minus 27, or negative 0.45. Now we evaluate dy at x sub 1 by substituting 27 in place of x and negative 0.45 in place of dx. And that will just give us negative 1/60, or approximately negative 0.167. So, take note that dy value is negative. Now, this would imply that the cube root of 26.55 is approximately 1/60 less than the value of y sub 1. And with this, we now can approximate on the cube root of 26.55 in terms of 3 minus 1 over 60, or that will be approximately 2.983. Okay, to summarize what we have today, that the differential of y denoted by dy is a product of f prime of x with the differential dx. That is, dy is equal to f prime of x dx. That the increment delta x is equal to the differential dx. However, the increment delta y is not equal to the differential dy, but can be approximated by dy for very small increment in x, that is, delta x approaches 0. That using local linear approximation, the value of some function can be approximated by using this formula, that y sub 2 is approximately equal to y sub 1 plus dy. Now that will be all for today. I hope to see you in the next lesson.